Good day. Thanks for joining me. My name is Peter C2. I'm an NRC authorized medical physicist, and today I'm going to be discussing high dose rate remote afterloaders and the regulations that you will need to have a handle on for your radiation safety purposes. I'd like to start with an introductory video from one of the open course softwares online that details some of the major steps of the process.
Now, we've already seen one type of radiotherapy, and we can refer to that as teletherapy, where the source of radiation is placed a long distance from the tumour or from the patient, and the patient is effectively irradiated from outside in. Now, that is one major type of radiotherapy. However, there is a second type of radiotherapy which dates from about the early part of the 20th century, and that is referred to as brachytherapy. Now, brachytherapy differs in concept entirely from teletherapy. Whereas teletherapy irradiates the patient from outside in, brachytherapy irradiates the patient from inside out. Very basically, we place a source of radiation, whatever that source may be, either close to, alongside, or actually inside the tumour tissue. And that can be used for a number of various sites.
Radiation therapy is delivered in 3 different ways. In most facilities with a cancer center, there is some sort of teletherapy machine, and usually it's a linear accelerator. Linear accelerators utilize high energy electric and magnetic fields to accelerate electrons to very close to the speed of light, and thereby create megavoltage photons and target the tumors by using some sort of image guidance system. And with that image guidance system, putting the tumor in the path of those high energy photons. Secondly, brachytherapy via sealed radioactive sources is implanted in lesions. That's the majority of the topic today, is high dose rate brachytherapy using a sealed iridium source. And sometimes those sources are implanted directly into the lesions, as in mold therapy or interstitial therapy, but more often than not, they're going to be put into applicators for practical applications. And then thirdly, the nuclear medicine solution, or solution therapy via unsealed radionuclides, where some sort of chelated radionuclide is mixed into a solution and injected or ingested by the patient. Typically, those are targeted either biologically or chemically. A number of different radionuclides are used in radiation therapy. In the course of sealed or unsealed therapy, the decay characteristics are listed on this slide here. In particular, we're going to be looking at 2 sources, one more likely to be used than the other, and those are cesium-137 and iridium-192. Both the cesium and the iridium have gamma rays that are emitted into 300 to 600 kV range, so there is a good bit of therapeutic energy deposited from each of the decays. Sealed sources for permanent implants are historically where the radiation therapy field started in using radioisotopes in sealed ways to get these treatment volumes done. They came in preloaded needles, or they were hot loaded on the spot during the course of the implant. This particular case is iodine-125. There's a photograph of the seed and a construction diagram of the seed showing the titanium capsule, and then the mathematical description of the dose points, which are used to generate a treatment plan. And that treatment plan is then translated to a 2D template. That 2D template is used to implant the needles, either the preloaded or the hot loaded seeds, through the perineum into the patient's prostate. And this is done with a transrectal ultrasound. Using sealed sources for temporary implants, specifically cesium-137, allowed us to make use of the afterloader. So sources are loaded into the applicator after the applicator is in place. Typically, some sort of ultrasound or fluoroscopic procedure allows us to verify the anatomical position of the applicator, and then the sources are going in. Frequently, until the case of the remote afterloaders, this was done manually by hand. So there was a good deal of exposure to the service personnel that actually handled and calibrated the sources, making sure that everything was where the physician wanted the prescription to be. On this slide, there is an example of the uterine cervix Fletcher suite that is used very commonly with both low dose rate and high dose rate applications. So the terms low dose rate and high dose rate are generated from a number of reports that describe the amount of dose received at the calculation point or at the surface of the target volume, and typically in number of gray per hour. The term low dose rate is for doses less than 1 gray per hour, and the term high dose rate is given to doses giving more than 10 gray per hour, understanding that a few hundred centigray can then be delivered in a few minutes. So typically prescriptions are on the order of 2 to 8 gray, and you can see that those treatments occur on the order of 20 minutes for the most part, depending on where the sources are in their lifetime. As demonstrated in the video, there are a number of afterloaders, and here's a sort of a picking of the ones that were on the market a number of years ago. There's a couple that aren't shown here. The newest VeriSource is not listed here. This is an older picture of the VeriSource in the bottom left. But the VeriSource and the GammaMed are the two produced by Varian Medical Systems. And then the Nucleotron/Elekta Microselectron VS and the Nucleotron Flexitron, which is their latest one. They all share common components, and those common components have to do with the management of the source, which is the topic of this discussion. The source is contained within a safe, and it is handled in a very precise fashion. The purpose of this outline is to talk about the advantages and disadvantages and potentially the features of these afterloaders when considering not using manual brachytherapy, not using hot loading. The advantages of having an HDR remote afterloader, well, the first one being that there is reduced radiation exposure to the medical and technical staff. So in the case of the Fletcher suite that was described above, it was a manual afterloader. That means after the applicator was placed inside the patient, then somebody would manually put those sources inside of the patient's applicator, including whatever spacers or whatever geometry concerns needed to have happen. So there is an increase in the radiation exposure to the medical and technical staff that come from having one of these low dose rate or medium dose rate brachytherapy procedures. Most of the time those procedures happen on an inpatient basis. So in addition to having the radiation oncology staff exposed, the medical staff of the supporting floor are often exposed. Number two, remote afterloading offers lower probability of misplacements or loss of the source during treatment. So for those that aren't familiar with it, oftentimes the manual afterloaders do not have any way to adjust where the source goes except for touching the source by itself or manhandling some sort of applicator or probe that is going to put the source in different places. The remote afterloader handles all the placement issues remotely or robotically, and the loss of a source during treatment is very unlikely as the source is welded onto a steel cable. Number three, with the use of Iridium 192, high dose rate remote afterloading devices yield greater than 200 centigray per minute and reduce the treatment time considerably when compared to the LDR placement. So 0.2 gray per minute or 200 centigray per minute, and they reduce the treatment time considerably when considered to LDR placements. LDR placements can last on the order of 2 days. Number four, the small diameter of the treatment source allows for tight curves and interstitial treatments and custom applications that are not easily accommodated with a typical LDR source. So there are several advantages. Along with advantages, there are disadvantages. So in having an HDR remote afterloader, you have to consider the cost of the suite, of the physical site where you're going to place the afterloader and all the necessary imaging. So construction, shielding, and all the ancillary position equipment is a modest capital expense, which is typically mid six figures in today's hospital economy. Number two, commonly, if you want to use an accelerator vault to get rid of some of these costs, you run into some scheduling conflicts. The time that it takes to do an HDR procedure actually is a bit longer than a standard treatment, so you have to work on some scheduling, and then there's the issues of multi-use in the same room. Number three, patient medical events still do occur, such as the misplacement of a source or the loss of a source, although much less frequently. And if they do, there is a higher potential exposure from this high dose rate source than any comparable low dose rate source. And number four, the long-term data for survivability and efficacy are based on the low dose rate numbers. And numerous treatment regimens that exist today frequently refer back to the equivalency in the terms of LDR studies. Or, as one physician told me, we have a lot of body of information about LDR, and we think that we have an HDR equivalency. This is a conversation to be had on a per physician basis. Independent of vendor, there are several features that all remote afterloaders share. So the first one is that there's a primary storage safe to contain the source when it's not in use. And the safe is typically a very large amount of high Z or heavy metal material that is probably the bulk of the weight of the afterloader. Number two, a mechanism to move the source from the storage safe to and from the applicator. Number three, a system to maintain the sources in the applicators for a set time and desired positions to determine those positions. Number four, a mechanism to return the source to the storage safe at the end of the treatment and during power failures or other emergencies. So in diagram format, here is the transfer tube that exits from the face of the applicator. Here is the transfer tube that exits to the face of the indexer. Same transfer tube. The indexer has an S-tube pathway, so there's no straight path going to a rotating joint. The rotating joint selects which one of the channels the source is going to go through. There is some sort of positioning system that counts the amount of distance and reflections on the cable, in this case, in this particular model, an LED with the photodiode, to show that the source is out in play or the dummy check cable is out in play. And then there's a large shielded housing. And in the shielded housing, the source and the check cable or the dummy or the simulator exist at the same point. Then the stepper motor is attached to both of these, and the stepper motor is very precisely encoded, or the voltage is known so that you know what the distance is based on how many volts this meter is read that's attached to this motor. And then for all emergency, there's emergency hand crank. So there's many redundant systems for the emergencies that potentially could occur. The emergency hand crank is sort of the last stop. Radium-192 is a man-made radioactive element that is produced by neutron activation of radium-191 in a nuclear reactor's neutron flux. It is the most common HDR source because of the ability to get high levels of specific activity. The half-life of the isotope is 73.8 days, which means that roughly every 90 days it's advantageous to change out the source in order to keep the source activity hot. Some facilities change it more frequently than 90 days. The treatment energy is a gamma photon that is about 380 keV or 0.38 MeV. So the distance is on the order of 5 to 10 cm practical treatment length. Okay, that does it for part one. I'm going to leave some questions, and we'll see you in just a few minutes.